part 2 of this session on an introduction to systematic reviews. So in this section we're going to focus mostly on how to read and interpret a meta-analysis or a forest plot. So just to refresh, for any clinical outcome that we're measuring, it can either be reported as a dichotomous outcome, which just basically means that there's only one of two options available, a yes-no type of approach, so yes-no, dead or alive, pregnant, not pregnant, etc. Or data can be presented on a continuous outcome or a continuous scale, so quality of life, pain, blood pressure, range of movement, etc. Okay, so the thing to note for particularly for forest plots and for meta-analysis, dichotomous outcomes will typically be presented as a relative risk and sometimes as an odds ratio, but pretty much you can interpret relative risk and odds ratio as fairly much a similar thing. So again, once again to recap, if you've got an odds ratio or a relative risk of 1, it indicates no difference between the two groups, the intervention and control. A relative risk below 1 represents a benefit, and a relative risk or an odds ratio above 1 represents a harm. Conversely, for continuous outcomes, we're looking at mean difference. So just the differences in the means between the intervention and the control group. So the only thing to really note here, unlike relative risk, the point of no difference is 0. So if you've got a mean difference of 0, it indicates no difference in outcomes between the two groups. Anything less than 0, so a negative number, usually means that there is some sort of benefit in terms of the intervention group. Whereas a mean difference above 0 usually indicates some sort of harmful effect as well. Okay, so what is a meta-analysis? So a meta-analysis, I guess in simple terms, is collating the results from various studies that you include in your systematic review in order to get one ultimate result, or a pooled effect, as we call it. Now, a meta-analysis, you just don't simply add up the numbers because that would negate for the various statistical properties of each study. So I'll talk about that in the next slide, but basically the meta-analysis component just relates to the addition of the results from the various studies that you've included in your particular systematic review. Okay, so here we have a forest plot. So a meta-analysis is a combination of all the articles. A forest plot is this graphical representation. They call it a forest plot because if you have enough of these, it sort of looks like a forest. Okay, so just to guide you on how to read a forest plot. So this is one looking at screening for colorectal cancer using the fecal occult blood test, or FOBT. The comparison is screening versus no screening or control, and the outcome is colorectal cancer. You don't have to worry about fixed. Sometimes it'll be fixed, sometimes random. This relates to statistical properties of the meta-analysis, something that we're not going to get involved in here. So on the left-hand side, we've got the studies that have been included in this particular meta-analysis. So you've got 1, 2, 3, 4 studies. So Funen, Gothenburg, Minnesota, and Nottingham. Here we have the intervention group, so screening. So we have the number, or represented by the small n, of people with the outcome, so that being colorectal cancer mortality. The big N representing the total number of participants in that arm of the study. So similarly here we've got the control group. Again, little n number of people with the outcome divided by a total number of people in the control group. So if you look at this first particular study by Funen, we've got 362 out of 30,967 people died of colorectal cancer in the screening group, as opposed to 431 out of 30,966 in the control group. And so that's represented across the 4 studies there. Now, in this case, we've got the odds ratio. So basically we're saying anything that includes 1, no benefit; anything less than 1, a benefit; anything above 1, a harm. So in this particular meta-analysis, you can plot the or represent the outcomes either graphically or numerically. So if we still look at Funen, we look at the plot here represented by the blue blob. If you look really closely, you can see the black line and the confidence intervals, or if you wanted to, you could just look at the odds ratio here. So here we have the odds ratio of 0.84, confidence interval 0.73 to 0.96. So basically this is telling us that this study identified a benefit. It's statistically significant, that benefit, because the confidence interval doesn't include 1. So you can obviously see that here, as well as see that here, because the confidence interval doesn't touch this line of no effect. And we could say that the odds of dying from colorectal cancer are reduced by 16% in the group that had the screening versus the no screening. Similar approach for the other 3 studies. You can either look at it graphically or numerically. So as I mentioned previously, a meta-analysis just doesn't add up the results from this study, this study, this study, and this study. And you can sort of see that graphically. So this particular study, Nottingham, seems to have a larger blue blob than, for instance, the study by Minnesota, which has a smaller blob. So the key component of a meta-analysis is that we don't add up simply results from all of the studies, and that's primarily because some studies have a larger sample size. So you'll notice the larger the blob, the more that particular study will contribute when we add up all of the studies. So this particular study, Nottingham and Funen, well, Nottingham contributes 42% to the overall meta-analysis, then Funen, and likewise as we go down to the sample size or smaller sample sizes. So this particular diamond down here is our meta-analysis, our pooled effect. So this is saying when we combine all of the studies together and account for the various sample sizes, this is the result we get. So just looking at it graphically, you can see that it's to the left, so it favours screening, doesn't touch 1 at all, so it's statistically significant. Alternatively, you can look at the numerical outcome. So the odds ratio is 0.84, confidence interval 0.78 to 0.90. So basically what we can say is when we combine the results of these 4 particular studies, it demonstrates that screening for colorectal cancer is reduces the screening for colorectal cancer reduces the odds of dying from colorectal cancer by 16%, and that difference is statistically beneficial. There's a whole bunch of statistics here that you can also look at. I'm not going to touch base on that at the moment because we don't really need to understand that. So the main thing that I want to get at is how to read this meta-analysis and how to identify what studies contributed to what. Similar sort of process, only this example is an example with continuous outcomes. So once again, we've got our title, so stretching to prevent or reduce muscle soreness after exercise. So this is looking at pre-exercise stretching versus not. and this is soreness on day 1. So as you can see, 3 studies. In this instance, if we take this first study called High, they've got 14 people in the stretching group, 16 people in the control group. This is the mean soreness or level of soreness on whatever scale that they use in the stretching group. This is the mean soreness level in the control group, and then this is our mean difference. So again, you can sort of see here, mean difference, yeah, it sort of favours stretching, but because the confidence intervals are so wide and they hit 1, it's not statistically significant. So not surprisingly, when you combine these 3 together, these 3 studies, this is the pooled effect that you get. Demonstrates that there's no real difference or no real benefit or harm from stretching, and that's because the confidence intervals here include 0. Okay, so what I wanted to do now is just highlight where the quality of evidence can be useful. So in the previous presentation, we talked about how systematic reviews critically appraise the quality of the articles included in their meta-analysis or their systematic review. This is how having that type of information can be useful in terms of conducting a meta-analysis. So this is the forest plot from one of the reviews on screening for breast cancer. So screening for breast cancer with mammography. Comparison is screening versus no screening, and the outcome is deaths attributed to breast cancer. So in this case, what the authors have done is said, look, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 studies that have been published on the merits of screening for breast cancer or not. 4 of these studies have been deemed to be of good quality, so they account for selection bias, performance, attrition, detection, and so on. The remaining studies were defined as poor or moderate quality studies. So what they've done is then broken up the meta-analysis into 2 parts. That's something that we call a sensitivity analysis, to see what effect, if any, the quality of the study has upon the outcomes. So on this slide, we'll just look at the 4 studies that the authors described as being good quality studies. So here they are, the 4. They're the results, and when you look at it, this is the overall pooled result. So the relative risk, or in this case risk ratio, it's the same thing, it's just UK versus US language. So the relative risk crosses 1. So if you look over at the relative risk, it's 0.93, so I would suggest some benefit. However, the confidence intervals include 1, and so it seems to demonstrate that there's no significant difference between screening and not screening in terms of reducing the number of deaths associated with breast cancer. Compare that to, let's say, the bad quality or the poor quality studies. So here are the 1, 2, 3, 4, 5, 6, 7 studies that were deemed to be of poorer quality. So they didn't account for selection bias or performance or attrition or detection. These are the individual results. This is the pooled meta-analysis, just for these 7 poor quality studies. So you can sort of see the conundrum that we're facing. The poor quality studies, when you look at them, the relative risk is 0.71, confidence interval is 0.61 to 0.83. So the poor quality evidence is actually telling us that screening for breast cancer is beneficial and it's statistically significant. So what do we do? What's the answer? And this is where clinical or content expertise comes into effect. The good quality studies are telling us that there's no benefit, there's not a whole lot of harm either associated with screening for breast cancer. The poor quality studies are telling us, yes, there is a benefit, and it is statistically significant. Sorry, it's up here. So when we combine the good quality studies with the poor quality studies, our overall result favours screening for breast cancer. And this is where there's a whole lot of debate at the moment, whether or not we should even be looking or taking into account this poor evidence, because there's this notion that, well, if you put garbage in terms of information, you're going to get garbage out in terms of results. So there's obviously a divide. Those that say, well, no, let's only stick to the good quality evidence and work on what that is telling us, as opposed to combining it with the poor quality evidence, which then potentially can skew the results. So this whole notion of systematic reviews has led, and the importance of them, was first introduced by a paediatrician, Archie Cochrane, who in the late 70s was very, very critical, saying, well, it's a damn shame that we don't have some sort of organisation that collates this information and makes it freely available to the public. And hence, the Cochrane collaboration was formed. So the Cochrane collaboration, some of you may have heard of it. That's the logo there, and hopefully now you'll appreciate. So that's the CEC, but that there is a meta-analysis, and it's a meta-analysis of the first systematic review that was done under the banner of Archie Cochrane. So you might hear this terminology of something being a Cochrane review. All that it means is that it's a systematic review that's been done under the guise of the Cochrane collaboration. And this particular review was one that he did. We've discussed it, but there was an issue around how to treat premature babies in terms of their lung maturation. Because if babies are born premature, lungs aren't matured, they'll die of, or there's a heightened risk of them dying from their premature death because of lack of respiratory function. So he collated the evidence on the use of glucocorticosteroids. First RCT available in 72. By 91, we had 7 trials. So when you look at it, the meta-analysis, it was fairly clear by the early 90s that we had sufficient evidence to give preemie babies corticosteroids to prevent death or increase their survival. So just quickly, one slide about the Cochrane collaboration. It's an entirely voluntary organisation. I've got a declaration to make. I am involved with the Cochrane collaboration, so I'm involved with the urology group. Everything's, or most things are done on a voluntary basis. There's well over now 20,000 people who conduct systematic reviews, and again, it's done in order to collate information and make it available in a usable form for people when they most need it. So I'll discuss about the Cochrane reviews and how people can use it, but just another thing whilst we're talking about meta-analysis, you can have what we call a cumulative meta-analysis. So this is an example of a cumulative meta-analysis, and with meta-analysis you don't necessarily need to have all RCTs. You can have meta-analysis of cohort studies, of case control studies, and so on. So this is a meta-analysis looking at passive smoking and whether or not it's harmful. and this is the real sort of, I guess, strength of a meta-analysis, and one that you can combine studies over a period of time. So this is looking at the relative risk of whether or not passive smoking is harmful. 1982, there are only 2 studies. didn't show any harm and certainly didn't show any benefit. 1983, another couple of studies were published, so now we've got 4 studies on the topic, and all of a sudden you see this pretty large shift. So it's above 1, so it's indicating, well, it might be harmful. A year later, 84, another 3 studies are published. You include them, now we've got 7 studies. What we see is the relative risk doesn't really change a whole lot, but as you'll see, the more studies that we've got, the tighter or the more precise the confidence intervals become. 85, 10 studies now, so confidence intervals get even smaller. 86, 12 studies, and so on, so on, so on, so on, so on. So we get to 1997, we've got 37 studies on passive smoking. As you can see, the relative risk hasn't really changed all that significantly over the 25-year period, but what has changed is the level of certainty, so the precision of our meta-analysis. So technically, one could argue, well, 1985, we had sufficient evidence to indicate that passive smoking was significantly harmful. Hasn't really changed by 1997, but what has changed is the certainty. So those confidence intervals are so tight that we can be fairly certain that we're seeing a true result there. So I was mentioning Cochrane review, the Cochrane collaboration, and why I guess we're so passionate about it, and that is that we want to provide evidence to those that need it, whether it be health professionals, policymakers, and just consumers in general, so they can access health information when they want it, in as much detail as they want it. So we're fairly lucky here in Australia that the Cochrane Library is freely available to everyone. So if you Google the Cochrane Library, you'll be able to access all systematic reviews that have ever been published by the Cochrane collaboration. The beauty about it is you can read a 1-page summary that's been specifically designed for lay people, so those with no health science experience whatsoever, or it can be as technical as what we've covered over the last few slides. I'd highly encourage you to have a click on that YouTube link if possible, just to view and to see how Cochrane collaboration and how systematic reviews were used some time ago now, when we had the disaster in Southeast Asia with the tsunamis and whatnot, and how we used evidence to inform practice and not needlessly waste resources, both monetary as well as physical resources, in the treatment of people in that aftermath of that particular disaster. So that wraps things up for this particular module and week. Once again, I just want to highlight the thing to get out of this particular session mostly is how to read a meta-analysis or the forest plot, and basically just recognise the strengths of conducting a meta-analysis. Thank you and enjoy.